Namah Shivaya. Myself, I'm Dr. J. Bala Vishnu, working as Assistant Professor Senior Grade in Department of Electronics and Communication in Amrita Vishwa Vidyapeetham, IT Campus, Coimbatore. So today I'm going to present the challenges in 5G technology. So this is the outline of our today's topic. And when coming into 5G topic, it comes into our mind in terms of increasing the bandwidth, reducing the latency, and increasing the number of connections. Okay. So the ITUT and IMT 2020 have given the 5G magic triangles, in which how the bandwidth is increased is given in terms of XMBB, that is extreme mobile broadband, and how to reduce the latency is given as URLLC, that means ultra reliable low latency communications. And for increasing the number of connections, they have given it as MMTC, that is massive machine type communications. So getting into this 5G, before that, let us discuss about that evolution or history about that 5G technologies. So we all know that it has been evolved from first generation to the current fourth generation, and the fifth generation is implemented in some cities. And coming for the first generation, so it is purely analog voices. Only for voice communications, we have used that first generation technology, and it is purely hardware, sorry, analog. And the data we have achieved in that first generation is about 2.4 kilobits per second. Whereas in 2G, whereas AMPS is the advanced mobile phone service we have used in the first generation. Whereas in second generation, we call it as an GSM, Global System for Mobile Communication, where we are along with your voice, that is purely digital voice, compared to your analog, it is purely digital. And you are also having an SMS, short message service. And apart from that, we are having some GPRS. That means your data is being transferred and received in terms of through internet. Okay, that is we are achieving about 64 kilobits per second in that second generation communications. So what improvement we had in our third generation around 2000, we had that third generation communication where we could achieve about 2000 kilobits per second. That means apart from our digital voice, SMS, and internet, we are increasing the data rate. That means you are increasing in terms of an image transmission receptions and audio songs we can download, audio transmission receptions, and also video transmission and receptions. We enhance the capability and improve that communications. And coming to our fourth generation existing, that is been called as an LTE, long-term evolution, where we furthermore enhance the performance in terms of data rate, and we are able to see on the video on demands like YouTube or many video channels are there, so through which we can access internet very fast, and voice over internet protocols, those helped, and many other technologies have developed, and with that we are achieving over 200 200 in terms of 10 power 6 kilobits per second. And coming to our fifth generation mobile communication, that is what we are going to see in future. In that, what we expect. So for that, in order to get into the 5G, so what we expect is that there are key specifications for that. There are apart from that data rate and the latency and the number of interconnections, we also look into that security, network slicing, and the ultra broadbands, and intelligent antennas, and battery powers, relay devices. So for example, if you take security, cyber security plays a key role in this 5G communications. And device density, the number of devices operating over an area is increasing day by day. That means in Internet of Things, each sensor is going to communicate, and with that, we are having more number of devices within a specific area. So, how to give up communication or a bandwidth access to all those devices? That also we need to consider. And coming to an battery power, so how we are going to increase that energy efficiency of a device? That means we are going to reduce that energy consumed for particular applications. So over a long duration, if you consume a lot of power, the battery gets drained and the energy efficiency will be low. So nowadays we need an device which is wireless, and also it should we should be able to operate it over a long duration. And even if it is for a week without charging, that is a good device. So we need. And like relay devices like cooperative communications. So relay devices will help that and improve that energy efficiency by playing a key role by having a cooperative communications between the source and the destination, or the transmitter and the receivers. So these are the other key specifications. So coming to the specification in terms of metrics. So first we look into the data rates. So what we are achieving in the long-term evolution, advanced long-term evolution, is that we are achieving about 150 megabits per second. But in 5G, what we expect is that we should achieve at least 20 gigabits per second of data rate. So in order to achieve such an high data rate, what technologies we are going to incorporate? That is the first key specifications. And the next key specifications is that the increasing the number of devices. That means device density should be more, densifications. So in 4G, the device density is very less. That means compared to 5G, we need an increased densifications of about 1 million devices per square kilometers. Whereas if we see in second generation, there are we have used GSM, Global System for Mobile Communication, with 20 megahertz of bandwidth distributed over for each node. We need a 200 kilohertz of bandwidth, so that we can adapt only 125 users per cell. Whereas what we expect in the 5G is that we are going to increase that the number of devices over 1 million devices per square kilometer. And next key specifications is with respect to the round trip delay, or we call it as an latency. So in existing LTE, we have an round trip delay of about 10 to 20 milliseconds for transmission, and the acknowledgement from the receiver, we takes about 20 milliseconds. Whereas what we expect to we expect the latency should be of 1 millisecond, which is very uh, uh, very difficult thing to achieve in terms of for latencies, which is 1 millisecond is it is very huge time. And coming to our battery life, so existing mobile communications, mobile sensors will be it is battery operated. So we, in order to improve your the lifetime of the battery, or in order to limit the charging over a day, we need to improve our battery lifetime in our fifth generation mobile communications. For that, in if you are having machine to machine communications and device to device communication, there it causes more, it consumes more power. So we are going to deal with this. And also what we are going to, what we are aiming at. So in overall, IMT advanced, what we look at LTE, that is fourth generation, and IMT 2020, what we look at fifth generation, is that there are difference which has been given by that ITU. And coming to our latency, what we have in LTE is about 10 milliseconds to 20 milliseconds. and what we expect is 1 milliseconds. And the device density, the connection density is about 10 power 5 number of devices per square kilometers. Whereas what we expect is that we are going to increase the density. That means number of devices have about 10 power 6 number of devices per square kilometers. And coming to our mobility, the mobility it means that over an kilometer per hour, if you are traveling at a higher rate, we are taking or if you are moving over a car or the pedestrian speaking through mobile, if you are calculating that speed, then if we are that LTE can able to give up about 350 kilometer per hour of mobility, whereas in many areas like that bullet trains, the speed of the bullet trains and many high speed cars will have about 400 kilometers per hour. So we are going to achieve it. So for that, how we are going to have a technologies to get that. That is also a main thing. And coming to the data rate is what we are going to aim at is that now currently they are having about 20 200 Mbps, 200 Mbps or about 100 Mbps. But what we are going to aim at is that it is of about 1 gigabits per second. That means is 10 power 9 of data rate. So, and coming to network energy efficiency, that means the ratio of the throughput divided by the energy consumed. It is given in terms of bits per second per hertz per joules. It is the ratio of throughput divided by the energy consumption. It is of about it is of about 100 times what we are going to achieve in that fifth generation communications. So this is all the key metrics for which we are going to consider, or the challenges what we face in fifth generation mobile communications. So with this key specifications, we can look at the applications of the 5G in terms of coming from smart mobiles in our packets. We are going to look at the smart home in our surroundings, like smart homes, and coming to our healthcare, smart health, and also we are having smart cities and smart businesses, and many places we are going to see this 5G. And what are the several new domains in order to achieve this thing is that by taking the different domains like augmented realities, Internet of Things, Internet of Vehicles, device to device vehicles, vehicle to vehicle communication, vehicle to everything, vehicle to infrastructure, and e-healthcare, machine to machine communications, artificial intelligence, and data analytics. So there are many places where this which there are many domains for which it can be done to achieve that high specifications. What we look at, what we aim at fifth generation mobile communication, and mainly the ECE are focusing on physical layer communications. So in our OSI model, we are having 7 layers. So coming from the first layer 1, physical layer, and layer 2, data link layer, layer 3, network layer, layer 4, transport layer, layer 5 is session layer, and layer 6 is presentation, and layer 7 is application layer. So mainly the ECE engineers will deal with physical layer and data link layer. So mainly the physical layer is or deal with the functionalities or the what we deal with the physical layer is that type of modulations, type of encoding, what is the channel, wired channel, wireless channels, what should be the transmission, how the transmission of bits will be. So those things are have been considered. Whereas in fifth generation, what physical layer technologies we are having. Whereas in fourth generation, modulations in physical layer, we are having the main modulations. What we are having is orthogonal frequency division multiplexing. So we are increasing the spectrum efficiency of our fourth generation by using this OFDM. But there are many reasons that OFDM or have the OFDM have limitations. So how we are going to deal with that limitations and how we are going to improve that. For that, there are many functionalities or the areas over which we are going to consider is that the millimeter first. We are going to look at millimeter wave wireless communications, and the second thing is massive MIMO, and the third functionality is like filter bank multi-carriers communications, and the fourth is the non-orthogonal multiple access. And apart from that, full duplex communication technologies also it plays a vital role in the physical AI technologies for the 5G mobile communications. And so why we need to enter into the millimeter wave band is that the band what we operate, like for example, if we are taking that industrial, scientific and medical application band, ISM bands, which operates at 2.4 gigahertz and 5 gigahertz, which is giving a bandwidth of about 200 kilohertz for the sensor network, plus 20 megahertz for that Wi-Fi communications, and for Bluetooth, it is having a different bandwidth and different transmission power is being allowed to transmit over that band. Whereas that band can give a maximum bandwidth of about 20 megahertz. So in order to increase that bandwidth over greater than 20 megahertz, what we need is that we have to shift into very high frequencies. So for that, what we are going to do is we are choosing that millimeter wave bands, in which millimeter wave we are having spectrum frequency band 1 and frequency band 2. The first we call it as in sub gigahertz, which is less than 6 gigahertz, and whereas next band is of about 54 gigahertz, which operates 7 to 64 gigahertz, which is having a high oxygen absorption rate. So we are going to eliminate that 57 to 64 gigahertz and also 164 to 200 gigahertz, which is having an water vapor absorptions. So if by eliminating that from 3 gigahertz to 57 gigahertz over a band of 54 gigahertz, and 64 to 164, we are having a bandwidth of 99 gigahertz, and we can use these bands till terahertz. So with this, we can have an availability of about 252 gigahertz of potential bandwidth with for 5G communications. So the main disadvantages of getting into that high bandwidth and high frequency is that line of sight communication should be achieved in fifth generation due to these high frequencies. When the frequencies get increased, the coverage region gets decreased, and also the attenuation, or sorry, the penetration through walls and penetration through some metallic objects, it gets varies, it get affected. So when we are going at higher frequencies, this bandwidth or these frequencies will not penetrate into that wall, penetrate into that some objects. So how we are going to overcome that? That is the main challenge in that millimeter wave spectral band communications. So when we are going for 5G, we are having at high frequencies. So this penetration is very difficult. So we have to maintain line of sight communications. And coming for this massive MIMO technology, so we already know that SISO, single input, single output, in which we are having only one transmitter antenna and one receiver antenna. Whereas what we felt difficult in that SISO is that we are having uh, less data rate and less reliability. So we can have two technologies to overcome the disadvantages. So one thing is by using multiplexing, we can increase the data rate. That means by transmitting, having many antennas for transmission and reception, we can achieve that multiplexing and diversity. So multiplexing is increasing the data rate. That means if you are using two antennas and transmitting 2 bits per second, we are increasing the data rate compared to ordinary one input, one output, SISO. So in previous SISO, we are achieving 1 bits per second. If you are assuming it 1 bits transmitted per second, we are achieving up 1 bps. Whereas with the MIMO of 2 cross 2, two antenna transmitted at two antenna at receivers, we can achieve 2 cross 2, we are achieving 2 bits per second. So similar to that, we can also have a diversity by transmitting the same data over the two antennas, where you can increase the reliability with either by transmitting the data multiple times, we can have a diversity in terms of time diversity, frequency diversity, and space diversity. But here we are having the space diversity, multiple input, multiple output of about 100 to 200 number of antennas, MIM. So by having multiple input, multiple output, we are having two things. One is reliability and another one is data rate. Reliability achieved through diversity and data rate achieved through the multiplexing. And here it is given that an base station with multiple antennas at that base station. With that multiple antenna, we can have an high data rate and also increased reliability. So that means we are reducing the BR versus BR curve, better rate, BR versus SNR curve, that we are having a better BR curve. And with that multiple antennas, we are having vertical beam forming and horizontal beam forming with an phased array to have an increased coverage area also. And next important technologies like FBMC, like which we call it as a filter bank multiple carrier. And the disadvantage what we felt in that orthogonal frequency division multiplexing is that it is having an less spectral efficiency due to that cyclic prefix, and also the peak average power ratio, which is the ratio of that power of the peak subcarrier, power of the subcarrier, which is having the maximum power divided by the average power of all the subcarriers. It has been calculated, and that plays a crucial role in designing the low noise amplifiers of a transmitter and receiver. And how to overcome that problem is that by using the filter bank to improve the resolution of each subcarriers, and also to reduce that intersymbol interference, which affects the other symbols, and also intercarrier interference. So this is been by designing a filter banks for each subcarriers, and it is achieved. And next important technology what we are having in fifth generation communication with respect to physical layer is that universal filter bank multi-carriers. So in universal filter bank multi-carrier, what we are going to do is that we are going to overcome the limitations of the filter bank multi-carrier by designing each filter for each subcarrier. Instead of that, what we can do is we can have a group of subcarriers. For that group of subcarriers, we are designing a filters. And if you are passing that group of subcarriers over a filter, then it gives a better PAPR, and we can reduce the complexity of the design of that systems. So this is the advantage of UFMC over the FPMC. And this is the comparisons made with respect to OFDM, FPMC, and UFMC. So what we are having is that these sharp lines, which shows that with an arrow, it indicates the subcarriers. So for all the subcarriers, we are having an filters in that OFDM, and we are having the problems. Okay, so in FBMC, we are going to filter each subcarrier and we are going to improve the performance. Whereas what the limitation is that the system complexity get increased. So for that, to avoid that, we are going for UFMC, where the group of subcarriers will be passed through a filter and we are using that interference caused due to other subcarriers affecting other subsequent subcarriers. And the main thing is we are improving that PAPR, and the main disadvantages is that the system complexity get increased, whereas that is reduced in the UFMC. And the other which we call it as a NOMA, which is a non-orthogonal multiple access techniques. So in OFDM, we are having an orthogonal frequency division multiplexing. It means each subcarrier is orthogonal to the next subcarrier, all the subcarriers, and by that we are having an transmission and reception at high spectral efficiency. So by increasing the spectral efficiency, we are having some disadvantages by having that property or orthogonality, and that is overcome that PAPR power problems and that orthogonality, the errors due to orthogonality is overcome by non-orthogonal multiple access. So in that, the non-orthogonal multiplexing techniques, what we are having is that we are having a base station at the transmitter side, and that transmitter side, instead of transmitting user one information alone within that subcarrier, what we are going to do is we are having both user one and user two's information added, and we are going to transmit it. So here we are assuming that user one is located nearby and user two is located far away. So user one, since it is nearby, it can receive the signal with the better signal strength, whereas user two, it receives the signal with the less signal strength. So in order to improve that signal strength at that the user two, what we are doing in the base station is that we are having a more power. In the graph, it is shown that user 2 is having more power compared to user 1. Since user 1 is located nearby, this power is sufficient to uh, reconstruct or retrieve the information of user 1. Whereas user 2, since it is located at far distance, we need more power to retrieve its information. So for that, what we have done is we have increased the power of user 2 and reduced the power, or the optimum power is allocated for user 1. At the receiver of user 1, what happens is that it receives both the user 1 and user 2 information, and by using successive interference cancellation techniques, it subtracts that user 2's signal and retrieves the user 1's signal from the received signal. So that is done by using successive interference cancellations. Whereas what happened in the user 2 is that it repeats the same thing. Since user 1 power is given with less power, it gets attenuated and that signal strength will be comparable with the noise, and the user 2's information will be better, will have a better signal strength, and it can retrieve at that receiver to user 2's receiver side. So this is the structure of the architecture of non-orthogonal multiple access techniques. And these are the references over which we have discussed this topic. And coming for our sixth generation communication. So again, what specifications we are going to look at the sixth generation is that we are increasing that frequency. So what problems we are going to face at 6 gigahertz. So increasing the frequency, it is given in the specifications like of about terahertz. So in fifth generation, it is given as sub gigahertz and of about gigahertz of communication, which is like an millimeter wave. Whereas what difficulty what we have faced is that penetrations. So in order to overcome that penetrations, what we need to do is that we are having a technology or materials to overcome that penetration by having an materials called IRS or RIS, which is intelligent reflective surface. So what the use of that IRS is that intelligent reflective surface, it receives the signal from that the base station, and the material will act as an which is an intelligent device. It reflects and it points towards that receiver if he is in indoor. For example, if there is no line of sight communication between the transmitter and receiver, then it is very difficult to achieve that line of sight communication. That means there is no direct path between the transmitter and receiver. So how we are going to achieve is that by using the intelligent reflective surface in between the transmitter and receiver, and the obstacle which causes uh, which uh, stops that frequency or very high frequencies in terms of terahertz, it will receive that signal, and it will also act as a relay, and it transmits it to back to that receiver side. So this we are combining all this cooperative communication, relaying. So these all things we are going to combine, and we are achieving this sixth generation communication. So with this, I'll finish the topic. And uh, so any queries?
Sir, there is no queries.
Okay. Yes, ma'am. Yes. Can I explain about the procedure for joining this?
Yes, sir.
Uh,
Yes, sir.
yes. So uh, in this in our Amrita Vishwa Vidyapeetham, we are given with an opportunity to join the M.Tech course in by using two ways. One is by using that by having a good gate score, and another one is that another method is through an interview by applying through university websites. So this is how we are going to apply for the MTech. In terms of there are three specialization in ECE. One is communication systems, and another one is automotive electronics, and VLSI, and biomedical. There are four branches, four specialization. For each specialization, you can have an valid gate score, and you can apply. And those who are not having valid gate score can apply through the website and can attend the interview to clear this the and to have an admission. Yes. Thank you.